reaction of some nucleophile and the carbonyl of an aldehyde or a ketone. Later in the chapter, we can turn the aldehyde or the ketone into a nucleophile by deprotonating alpha to the carbonyl. But to start off, we're going to use that carbonyl as the electrophile, and we are going to attack it with some sort of nucleophile. If your nucleophile is electronegative, like if you've got some oxygen containing nucleophile, like maybe water or an alcohol or something like that, or a nitrogen containing nucleophile, like some sort of amine, then the tetrahedral intermediate is not going to be stable, and you're going to end up eliminating one unit of water or one equivalent of water from the addition product. And so let's see what we're talking about there. So we'll just draw our generic ketone again. The other thing worth noting is that theoretically we draw all these things like, hey, that ketone's getting attacked by the nucleophile. In reality, if you're the person in the lab doing this reaction, very often you actually have to activate the carbonyl. And by that I mean you have to allow it to react with some sort of source of a proton, right? We have to protonate the oxygen. It makes that carbon even more electrophilic, because if the oxygen has a positive charge, right, because we protonated it, and that carbon's already partially positively charged. If we attack the carbon and dump the electrons from that double bond into the oxygen, we quench the positive charge. So if you've got a nucleophile that is particularly electronegative, so, those electrons are more tightly held by the nucleophile and less maybe available to attack your electrophile, or say those R groups have electron, releasing groups on them, and so that partially positive carbon isn't so big, we can hit this with an equivalent, and very often we'll draw our acids like this, HB, okay? So we'll draw our our acid, and the only reason I draw it that way is so that I can keep track of the conjugate base, because I will use it again. After you get used to drawing a bunch of these mechanisms, you don't often have to write HB. You just write H+. And then in the back of your mind, its conjugate base is still in the flask. But when you're first getting used to doing it, it's nice to keep track of everything. If I protonate this, I activate that carbonyl. I make that carbon just a little hotter for nucleophilic attack. See? Now, if I've got some electronegative nucleophile coming in, let's just use something simple like ammonia. Right? It has a lone pair of electrons. Why not? When this comes in and attacks the carbonyl, we're going to push those electrons up into that oxygen and quench that positive charge. And I form a tetrahedral intermediate. But notice how I've gone from sp2 to sp3 hybridization. Make this just a little bit more suggestive. Okay? So remember when we used HB for our acid? This is catalytic in acid, most of these reactions, right? We're going to catalyze the reaction. So you're going to speed up the rate of the reaction. You're not going to move the equilibrium, right? So adding the acid is not going to make more product, right? We're not changing the equilibrium of the reaction. We're just speeding up the rate. We're messing around with the kinetics, getting this thing to go a little bit faster, right? But if it's a catalyst, if the acid's a catalyst, it has to come back at the end of the reaction, unscathed. So I'm going to take the conjugate base of whatever acid it was that I used at the beginning there, and I'm just going to deprotonate this. I'm going to return electrons to the nitrogen. And I'll get this species here. Now guess what I have in the flask again, you guys? Acid. So I've got the acid back. I'm going to take the electrons on the oxygen and I'm going to attack that acidic hydrogen. So then what do I get? I get now we've got water there, right? That's a pretty good leaving group. Let me redraw this amine down here just a little bit more suggestively. There you go. When I deprotonated that acid, what do I have left now? I have its conjugate base, don't I? Well, I can take that conjugate base, and if I deprotonate this, these electrons can form a double bond between that nitrogen and that carbon, and then water leaves. I have an E2, don't I? I'm going to draw this, I'm going to bring the nitrogen up so it's a little easier to see. Plus water. See how water was eliminated from the addition product. So our tetrahedral intermediate, when we have a little bit more of an electronegative nucleophile, like an oxygen or a nitrogen, the tetrahedral intermediate is not going to be stable. And so we're going to end up doing a little shuffling around of these protons. And we're going to eliminate one equivalent of water, and we make a totally new functional group. And we'll talk a little bit more about that functional group in a bit, but that is an example of an electronegative nucleophile adding to either a ketone or an aldehyde. And so the aldehydes are going to be a little bit more reactive than the ketones. In fact, the aldehydes can sometimes be so reactive that you end up with a pile of different byproducts. You know, we can easily just say theoretically, you know, on the chalkboard or whatever, on a piece of paper, here you go, here's the mechanism, and here's the product that I get. But in reality, you're the person standing in the fume hood doing the chemistry, and you're like, and, you know, there's, sure, that product and these 4 other things that happened, you know. So if your electrophile is particularly, or even if, you know, we turned it into a nucleophile, particularly reactive, you're going to have all kinds of side reactions happening. But it's easy to draw, theoretically, the product that you're supposed to get. So let's do a couple of examples. I'd like to break these into sections. So if you don't mind, I'm going to start out with carbon nucleophiles because it's really closely reminiscent of a couple of reactions that we just covered, one of which we covered, I think, in chapter 3 when we were talking about alkynes. We just talked about the Grignard reagent when we did ethers. And then I've got another reaction that I want to share with you. And the addition of hydrogen cyanide. So we're going to be forming carbon-carbon bonds in this case, right? So the addition of a carbon nucleophile. In the next video, I think I'm going to start talking about probably nitrogen nucleophiles. And that'll be a thing all by itself because there's a whole pile of other functional groups that fall out of that. And then I want to move on from there to do a video just on oxygen-containing nucleophiles. And then we'll end up polishing off the chapter by turning these aldehydes and ketones into nucleophiles and doing a couple of reactions like that. So let's start out with our first example here. And I decided to do the Grignard first because we just did it in the chapter on ethers, where ether was a solvent, right? We know a Grignard reagent is simply just some sort of alkyl or aryl nucleophile, right? So it's mostly just either R minus or, you know, AR minus. And so there's a couple of ways here that we have to react these Grignard reagents. We can either react them with formaldehyde, so the simplest of all aldehydes. So plain old formaldehyde. And I can hit this with just, you know, pick your old garden variety Grignard reagent. Doesn't really matter. Right? But this thing acts like this. Remember that? So our nucleophile is this thing here. What are we going to get on the other side? Now, after we allow these to react, and we can draw this all sort of like in one step, we're going to add some acid at the end there. And we're going to get what? We're going to attack the carbon of the carbonyl on the formaldehyde. And then we're adding what? We're adding 1, 2, 3 carbons in our Grignard. And then there's 1 carbon in the aldehyde. So we're going to have something that's got 4 carbons. There's your 4 carbons. And after we add that acid, a hydroxyl group. So we end up with a primary alcohol. If we take this Grignard reagent and we react it with formaldehyde, what if I wanted to react some other kind of an aldehyde with a Grignard reagent? Well, if it's not formaldehyde, I'm getting a secondary alcohol, right? So I can take some other garden variety aldehyde. What makes it secondary? The alcohol, that R group on the formaldehyde or on the aldehyde. I'll just use the same Grignard just to keep things easy to see. We're going to work this up with acid after the reaction is done. When we say work it up, I don't know how many labs you guys actually got to do, but at the end, when you're doing a synthesis reaction, very often you'll do some sort of extraction or some kind of a separation, where you're going to shake something up under either acidic or basic conditions. What you're doing at the end there, that's the workup. And very often this acid is added then. It's not like you're doing this in the flask, right? So you're going to react to the Grignard reagent with the aldehyde, and then when you work it up, you'll work it up under acidic conditions. And chemistry happens in the separatory funnel, so that's fine. I'm going to take my R group there just to see where we were. And then I've got here is the carbon, right, that I'm going to bond to the carbonyl of the aldehyde. So what do I have? I've got 1, 2, 3 carbons in the Grignard and 1 carbon at the carbonyl and then the R group. So this is going to be 4 carbons after the R group. 1, 2, 3, 4, right? 1, 2, 3, 4. And then what? So I have to make sure that I have the 4 carbons. So don't just put the hydroxyl group there. I've got 1, 2, 3, 4, and then sorry, the hydroxyl group is over here. It was on the carbonyl. So 1, 2, 3, 4 carbons. Yep. So we have a secondary alcohol. This is a standard Grignard reaction, right? What happened? Well, we can draw out a mechanism for this down below here if you like. So what happened? Well, let's see. I'll do the reaction that I just had there. So I'm going to take the Grignard, and this is going to react like this. Right? This is going to come up here, attack this, push electrons up into the oxygen, and I get what? I get this tetrahedral intermediate. This is where the acidic workup comes in. So what did I just add? 3 carbons. 1, 2, 3, right? 3 carbons. Let's highlight these. This right here is this right here. Okay? Now, the acid. What's going on with that? Well, there's a negative charge here. That H3O plus, right, is good for a proton. Protonated water, right? It's acid-base reaction, so we got this equilibrium happening. And then what do I have? I've protonated the oxygen, and then I have what? The hydrogen's implied, isn't it? So then I've got 1, 2, 3 carbons. And again, there you go. There's that carbon from the Grignard. So it's a pretty simple mechanism, right? What if I want to make a tertiary alcohol? Well, why don't I react a ketone? So I have an extra R group. And it's the same old, right? So garden variety ketone and a Grignard. Let's just use the same Grignard. Why not, right? Acid workup. Then I get this. Same mechanism. This right here is this right here, right? And this right here is this right here. So we formed a bond between those two carbons using a carbon nucleophile. All right. We got another example of a carbon nucleophile down here in the acetylide ion. So remember way back in chapter, I think 3, when we covered alkenes and alkynes, we talked about creating the acetylide ion. We got a nice strong base and an alkyne. So let's just draw one of those. We'll make our acetylide ion so that we all remember what we're talking about here. So there's my alkyne. And I'm going to use a nice strong base. So like sodium amide. And ammonia. What do I get? I'm going to deprotonate the end of this alkyne, aren't I? And I get that. This is the acetylide ion. I can react this thing with, say, some kind of aldehyde or ketone, take your pick. What's going to end up happening after workup is I will get what I'm going to add on to the carbonyl. So I've got R. We'll protonate that with the acid. The hydrogen will be implied. And then what? So I'm going to be adding this right here. Here's the nucleophile. Right? So I'll draw that in, that carbon, and then that right there was the nucleophilic carbon. And after we protonate the oxygen, we get the alcohol. But the acetylide ion, right, this is going to react just like you'd expect. So let me draw down here what's going on. And I'll draw it backwards so it's easier to see. Negatively charged carbon there. These electrons are going to attack that carbonyl carbon, push electrons up into the oxygen. We get our tetrahedral intermediate. I'll draw the hydrogen in just for the hell of it, but it's usually implied. But it's nice, to see that it's a tetrahedron. We've gone from sp2 hybridized carbon to an sp3 hybridized carbon. So we've got the carbon that was from the acetylide ion, right? And then the triple bond to the other carbon, and then whatever's hanging off of that. Now we're going to protonate this. Toss this into a SEP funnel, right? And protonate that oxygen, and we get our product. If you're wondering why I'm drawing this in a straight line, it's the triple bond there. This thing is The bond angle is 180 degrees. Okay. So the last example for the carbon nucleophiles that I want to give to you, I want to talk about this reaction a little bit. I've done a couple of these. And so in theory, we could just say, have at it, add, hydrogen cyanide to your aldehyde. But here's the deal. Hydrogen cyanide is a pretty toxic little gas. So this right here, this is a toxic gas, right? It's HCN. So it's in your best interest as the chemist to actually make this thing in situ. And by that, I mean, let your aldehyde swim around in the presence of, say, some hydrochloric acid and a source of the cyanide ion, like sodium cyanide or potassium cyanide or whatever. And it's a cool little reaction because the salt, the sodium cyanide or the potassium cyanide, is not going to be soluble in an organic solvent. So you're probably going to put that into some aqueous solution with the hydrochloric acid. And then you put your aldehyde into, say, some ether or whatever, right? And so the ether and the water are not going to mix. You'll have these two layers. And at the interface between the two layers, you'll have your chemistry happening. That's where your reagents are going to come and meet each other. And your product will be ether soluble. So it pulls the reagents out of the aqueous phase, right? Just at the interface between those two layers. And when you get your product, it goes down into the organic layer, and then all you have to do is stick it into a set funnel and extract. But you don't necessarily want to be, manhandling hydrogen cyanide. You want to create it in the pot, away from you, in the fume hood, right? So, but we can draw anything we want on paper. So let's just draw our aldehyde. Generic aldehyde here. And what you're going to do is you're going to first react this with the cyanide. So say sodium cyanide. And what does that look like? It looks like this. We'll just draw this out for you to see. The negative charge is on the carbon, right? We're going to attack the carbonyl with the cyanide ion and push electrons up to the oxygen. Notice how we're just able to do this, right? So our electrophile is that aldehyde, and the nucleophile is not particularly electronegative, right? So it's pretty nucleophilic. So we don't have to really activate the carbonyl all that much. Sometimes you do. So I get this intermediate. I'll draw the hydrogen in. And then the hydrogen cyanide comes in. So we've created this in situ, so in the flask, right? And we're going to protonate that oxygen. This has a name. Sometimes you just see it as like the nitrile group, so just CN or whatever. I put the triple bond in there so you can see what it looks like. This thing is called, and now depending on what the R group is, right? But the functionality that is explicitly drawn out for you, this is a cyanohydrin. And I should probably draw these arrows. This whole thing is reversible. And I've got a story to tell you about that. I did this reaction one time, not this like R, but it was a specific cyanohydrin that I made. And I ran it down a column after I was done to purify it, and it took me 10 hours because I had a ton of material to purify. Can we just talk about the reversibility of this reaction? At the end of 10 hours, I had the cleanest, most gorgeous aldehyde back again. Yes, the cyanohydrin is pretty sensitive. And so running it down a column of silica gel, I basically turned it back into the aldehyde and had no idea until it was all nice and dry and gorgeous looking. And I went and got an NMR and I was staring at my starting material. You guys, the tears that I cried that day. Anyways, I could tell you this story, and you could go into the lab and not even think twice about it, and just, I'm going to purify my product, run it down a column, and boom, you get your aldehyde back again. It's just one of the sad days in the organic lab. But anyways, that is another example of a carbon nucleophile. I'm going to stick to these three for this chapter. There's a lot of chemistry going on in this particular chapter, so we're going to stick to three carbon-containing nucleophiles. In the next video, I want to share with you nitrogen-containing nucleophiles. And you guys, there's going to be a whole pile of new functional groups that come out of this. So I'm going to let that be its own lecture. And then after that, we'll focus on the oxygen-containing nucleophiles.